What happens at the exact moment a black hole is born? Welcome back to Summarize Science. Today, we're looking at the razor's edge of gravitational collapse, a concept so precise it's called the critical threshold. For decades, physicists have known that at this tipping point, matter behaves in a universal way, creating a repeating, echoing pattern as it collapses, regardless of how you start it. It's like a secret code embedded in the laws of gravity. But most studies were done with simple, spherically symmetric matter. This paper investigates a more realistic scenario by adding spin, or what physicists call twist, and angular momentum, to the collapsing field. They used powerful supercomputer simulations to see what happens right at that critical moment. They first looked at a simple mode of spin and confirmed the results of earlier work. The universal echoing pattern was still there. But then they simulated a higher mode of spin, a more complex pattern. They discovered something fascinating. The universal behavior was still present, but the fingerprint, the specific period of the echoes, and the scaling of the black hole's mass was completely different. This means that while universality is a real feature of gravity, it's not a single rule for all situations. Instead, each class of spinning collapse seems to have its own unique, universal signature. The researchers also tackled a huge question. Can extremal black holes, those spinning at the absolute maximum speed allowed by physics, form from this kind of collapse? You might think that adding more spin to the initial matter would create faster spinning black holes. But their simulations showed the exact opposite. As they got closer and closer to the critical tipping point, the black holes that formed had less and less spin, eventually approaching zero. This suggests that for these scenarios, nature avoids creating extremal black holes. Another interesting result came from comparing this to studies without spin, where the collapse can get messy, with a competition between matter collapsing and pure gravitational waves collapsing. In this new work, adding spin seemed to tame the process, forcing everything to collapse neatly toward a single center without any competition. So, let's recap the key takeaways. First, the universal rules of critical collapse are real, but they change depending on the pattern of spin involved. Second, this type of collapse doesn't seem to be a pathway to forming maximally spinning or extremal black holes. And third, adding spin appears to simplify the collapse process, removing the chaotic competition seen in other scenarios. This incredible research provides a deeper and more nuanced understanding of how black holes form. It tells physicists that the rules of gravity are more complex than previously thought and gives them new directions for future research into the extreme limits of the universe. Thanks for joining us on Summarize Science.